AI Tokenization Deep Dive: How Senior Engineers Master Text-to-Token Pipelines in Modern AI Systems. Welcome back to Agentic AI World. I'm your host, and this is episode 67 of your daily AI interview prep series. Today we're going deep on tokenization, one of those foundational topics that interviewers love because most candidates treat it as a black box. Senior engineers don't. Let's fix that. Section 1. What is tokenization and why does it matter? Tokenization is the process of converting raw text into the numerical units, called tokens, that a language model actually processes. Before any text reaches an attention layer, it goes through a tokenizer. Get this wrong, and everything downstream breaks. Most candidates know the surface answer. We split text into tokens. But interviewers want you to go deeper. What algorithm? Why that algorithm? What are the trade-offs? Here's the key insight. Tokenization is a compression problem. You want a vocabulary that covers as much natural language as possible with as few tokens as possible, while keeping the vocabulary size manageable. Too small a vocab, and every word becomes many tokens. Too large, and your embedding matrix becomes a memory nightmare. Section 2. The three major tokenization algorithms. The first algorithm is byte pair encoding, or BPE. This is used by GPT-2, GPT-3, GPT-4, and most OpenAI models. The algorithm starts with individual characters, then iteratively merges the most frequent adjacent pairs into new vocabulary entries. You end up with a vocabulary of common subwords. BPE is great for English-heavy corpora. The weakness? It's greedy and corpus-dependent. The merge rules are baked in at training time, which means the tokenizer can struggle with languages or domains that weren't well represented in training. The second algorithm is WordPiece. This is what BERT uses. Similar to BPE and Spirit, but instead of merging the most frequent pair, it merges the pair that maximizes the likelihood of the training corpus. It adds a special hashtag prefix to tokens that continue a word, helping the model track word boundaries. The third algorithm is Unigram Language Model tokenization, used by SentencePiece and models like T5 and Albert. Instead of building up from characters, it starts with a large candidate vocabulary and prunes tokens that hurt the overall likelihood the least. This gives a probabilistic foundation and naturally handles multiple languages. Section 3. Byte-level BPE and Unicode handling. Here's something that trips up senior candidates. How does a tokenizer handle arbitrary Unicode or emoji? OpenAI's TikToken uses byte-level BPE. Instead of characters, the base units are the 256 possible byte values. This means the tokenizer is guaranteed to handle any valid UTF-8 string, no unknown tokens, no UNK fallback. The trade-off: byte-level encoding makes rare characters very expensive in tokens. A single emoji might cost 1 token if it's common, or 5 tokens if it's rare. Chinese characters that aren't in the vocabulary can cost 3 to 4 tokens each. This has real production implications. If your application processes multilingual text at scale, you need to account for this in cost estimation. A 1,000-character English document might be 250 tokens. The same length in Thai could be 800 tokens. Section 4. Context window and tokenization strategy. In a system design interview, you'll often need to think about how tokenization interacts with context window limits. The rule of thumb for English is roughly 4 characters per token. But for code, it can drop to 2 to 3 characters per token because identifiers and symbols don't compress as well. For JSON, you pay a heavy price for repeated keys. Senior engineers know to pre-compute token counts before sending to the API. You never want a runtime truncation error in production. The right pattern is: 1. Estimate tokens at ingestion time and store them with your documents. 2. At retrieval time, use token counts to fill the context window precisely. 3. Implement a sliding window or hierarchical summarization for long documents. Section 5. Vocabulary size and its trade-offs. Why does vocabulary size matter? Because every token in the vocabulary gets its own embedding vector. GPT-4 uses roughly 100,000 tokens. Each token needs an embedding, typically 4,096 or 8,192 dimensions in large models. That's 100,000 times 8192 by 4 bytes equals over 3 gigabytes just for the embedding layer. Larger vocabulary, better coverage of rare words, fewer tokens per document, lower inference cost. But also larger model, slower initialization, more sparse gradient updates during fine-tuning. Smaller vocabulary, more tokens per document, higher inference cost, but faster training on smaller datasets. For fine-tuning on a domain-specific corpus, say, medical records or legal documents. You might consider extending the tokenizer vocabulary with domain terms. This is called tokenizer extension. You add new tokens, resize the embedding matrix, and initialize new embeddings either randomly or from the average of their constituent subword tokens. This is a non-trivial engineering task, but can meaningfully improve downstream performance. Section 6. Special tokens and their role. Every production tokenizer has special tokens. These are reserved vocabulary entries that control model behavior rather than represent text. Common ones. BOS is the beginning of sequence token. EOS is end of sequence. PAD is for batch padding. SEP is the separator in models like BERT. And increasingly, models use custom special tokens for system prompts, tool calls, and structured output markers. When you're fine-tuning, how you handle special tokens matters enormously. If you train on data where special tokens are present but incorrectly placed, the model learns the wrong boundary signals. A common bug, forgetting to add the EOS token to training examples, which causes the model to never learn to stop generating. Section 7. Interview questions and how to nail them. Let's walk through 3 interview questions you're likely to face. Question 1. How would you handle tokenization for a multilingual customer support system? Strong answer. Use a multilingual tokenizer like the one in mbird or XLM RoboArta, which was trained on balanced multilingual data. Profile token costs per language in your corpus. For high-traffic languages with poor tokenization efficiency, consider a language-specific tokenizer and routing layer. Cache tokenized inputs to avoid re-tokenizing the same documents. Question 2. Our RAG system is returning context that sometimes gets cut off mid-sentence. What's happening and how do you fix it? Strong answer. The retrieval layer is operating on character or word counts, not token counts. When the retrieved chunks are assembled, the token limit gets exceeded and the final chunk is hard truncated. Fix. Compute token counts at index time and enforce token-aware chunking. Add a safety buffer of 10 to 15% for the assembly step. Question 3. We're seeing high latency on our LLM inference. What tokenization-related optimizations would you look at? Strong answer. First, check if you're re-tokenizing the same system prompt on every request. Use prefix caching or pre-tokenize in cache. Second, check your vocabulary coverage for your domain. Poor tokenization efficiency means more tokens, which means longer sequences, which means quadratically more attention computation. Third, consider whether you can truncate or compress inputs at the tokenizer level before they reach the model. Section 8. The mental model senior engineers use. Here's the mental model that ties this together. Think of the tokenizer as the API contract between human language and the model's internal representation. Every design decision, vocabulary size, algorithm, special tokens, byte level versus character level, is an engineering trade-off between coverage, efficiency, and cost. Senior engineers don't just use tokenizers. They understand the trade-offs well enough to make informed decisions when the defaults fail. When you're in an interview and tokenization comes up, show that you've thought about it from 3 angles. Correctness. Does the tokenizer handle all inputs without errors? Efficiency. What's the token cost, and how does it affect latency and price? And behavior. How do special tokens and vocabulary choices affect model outputs? That's episode 67. Today's topic was tokenization, from BP to byte-level encoding to context window math to interview questions. Tomorrow we'll go deep on another cornerstone of production AI systems. Subscribe so you don't miss it. If this helped you, share it with an engineer preparing for their next AI interview. That's the best compliment you can give. I'll see you tomorrow. Keep building.